In the next 10 minutes, I'm going to explain if two diodes are connected in series connection, how to find out the supply current and diode voltages in terms of supply voltage and their saturation currents. And if we wish to increase the supply current by a factor of 10, we'll calculate what is the required supply voltage. And after that, considering this circuit, if Is is given, how to find out diode voltage and supply current if the Vx is changed from 0.5 to 1.2 volt. For that, if the cross-section area of D1 is increased by a factor of 10, we will also determine the diode voltage and supply current for 0.8 and 1.2 supply voltages. So now let's start with the 17th question. They say that figure 2.41 shows two diodes with reverse saturation currents of Is1 and Is2 placed in series. We need to find out IB, VD1, VD2 in terms of VB, IB and Is1 and Is2. So these two diodes are separate diodes. They have different saturation currents. So we know that VB is VD1 plus VD2. VD1 is VT ln IB by Is1 plus VD2 is VT ln IB by Is2. Okay, so this can be written as VT ln IB square by Is1 Is2. If we write IB as Is1 and Is2 under root exponential of VB by 2VT. Yeah, so we have derived the supply current in terms of Is1, Is2 and VB. Next, we need to find out VD1 in terms of IB, in terms of VB, Is1, Is2. So VD1 can be written as VT ln IB by Is1. So it's VT ln substituting IB value, it's Is1, Is2 under root by Is1 and exponential of VB by 2VT. So it's Is2 by Is1 under root ln exponential will be cancelled, VT will be cancelled, that will be VB by 2. So it is VT ln Is2 by Is1 plus VB by 2. Similarly, VD2 will be VT ln Is1 by Is2 plus VB by 2. Okay, now that we have calculated supply current and diode voltages, now let's find out the next part. It says in the circuit of problem 17, we wish to increase IB by a factor of 10. What is the required change in VB? So now let's write the relation of VB with IB. So VB is VT ln IB square by Is1 plus Is2. So IB is increased by a factor of 10. So VB dash will be VT ln 10 IB whole square, that is 100 IB by Is1 Is2. Okay, so now separating these two, we'll get VT ln IB by Is1 Is2 plus it will be VT ln 100. So VT will be 26 millivolt at 300 Kelvin into ln 100. It will be 0.119 volt. This is our previous VB. This will be our extra voltage. So the change required in supply voltage will be 0.119 volt. Okay. Now they say that consider the circuit shown in figure 2.42 where Is is given. We need to calculate diode voltage and supply current for the change in Vx from 0.5 volt to 1.2 volt. Okay. Yeah, now let's write one KVL equation. That will be Vx equals to Ix R1 plus Vd1. So Ix will be Vx minus Vd1 by R1, where Vd1 will be Vt ln Ix by Is1. Now for Vx equals to 0.5. For Vx equals to 0.5, the diode will not turn on because it needs a minimum of 0.8 volt and greater than that. So if you see here, 0.5 volt. Okay, so initially the diode is turned off. So if you supply 0.5 volt, there will be no current passing through this, so it will be 0.5 volt. The diode won't turn on. So the voltage appeared across the diode will be 0.5 volt. So the voltage appeared across the diode initially will be 0.5 volt. Okay. So Ix will be 0 and Vd will be, now we can't calculate Ix equals to 0 in this equation. So Vd will be 0.5 volt only. Now Vx equals to 0.8 volt. So our Ix will be 0.8 minus, we need to take previous Vd value, 0.5 by R1 will be 2000. It is 0.8 minus 0.5 by 2000. It's 150 microampere. Okay, putting this value here, we get Vd1 equals to 26 millivolt ln 150 microampere, 2 into 10 power minus 15. 26 into 10 power minus 3 ln 150 into 10 power minus 6 by 2 into 10 power minus 15. It is 0.651 volt. So for Ix equals to 150 microampere, Vd1 will be 0.651 volt. For a Vx equals to 0.8 volt. Now let's say Vx equals to 1.0 volt. Our Ix will be 1.0 minus previous Vd1 value, it's 0.651 by R value, it's 2000. It will be 1 minus 0.651 by 2000. So it is 174.5 microampere. Using this value, we need to calculate Vd2. This is Vt ln 174.5 microampere by 2 into 10 power minus 15. 26 into 10 power minus 3. 174.5 into 10 power minus 6 by 2 into 10 power minus 15. It's 0.654 volt. And for Vx equals to 1.2 volt, Ix will be 1.2 minus 0.654 by 2k. 1.2 0.654 by 2000. It's 273 microampere. Vd3 will be Vt ln 273 microampere by 2 into 10 power minus 15. The value is 26 into 10 power minus 3 ln 273 into 10 power minus 6 by 2 into 10 power minus 15. It is 0.666 volt. Okay. Usually for each value we need to do multiple iterations, but I'm doing only one iteration now. So if you want, you can do more iterations. Like if you take 0.666 volt, you can calculate Ix again with 1.2. Like you can do Ix equals to 1.2 minus, now the previous value becomes this 0.666 by 2000. 1.2 minus 0.666 by 2000. It is 267 microampere. If you put this value and calculate VD4, it's 26 into 10 power minus 3 ln 267 into 10 power minus 6 by 2 into 10 power minus 15. It's the same, 0.666. If the new VD value is same as the previous VD value, that means that you have arrived at the optimized value. So we need to do multiple times the iterations to get the optimized value, the accurate value. Okay. So the next question says, in the circuit of figure 2.42, the cross-section area of D1 is increased by a factor of 10. We need to determine VD1 and Ix for Vx equals to 0.8 volt and 1.2 volt. So the Is becomes 10 times of Is. Now it's the same. Ix will be Vx minus Vd by R1, and Vd will be Vt ln Ix by Is1. So our Vx will be 0.8, it is given. Let's calculate Ix. Let's start with the Vd is equals to 0.768 volt. So it will be 0.8 minus 0.768 by 2k. This will be 160 microampere. Vd will be 26 into 10 power minus 3 into ln 160 microampere by Is will be 10 times of the old one. It's 2 into 10 power minus 15. Let's calculate this. 26 into 10 power minus 3 ln 160 into 10 power minus 6 by 10 into 2 into 10 power minus 15 is 0.5928 volt. Now let's calculate for 1.2 volt. Now I'm doing this for only one iteration. You can use newly calculated VD value here to get a new calculated Ix value and use the same for calculation of VD. So this will be calculated iteratively. You need to do this until you get a new IXID values same as that of the old ones. So that will be the accurate IXID values. Let's do it for 1.2 volt. Now Ix will be 1.2 minus 0. Let's take this value, newly calculated value instead of the starting value, 0.5928 by 2k. It will be 1.2 minus 0.5928 by 2k. It is 303 microampere. Vd will be 26 into 10 power minus 3 ln 303 into 10 power minus 6 by 10 into 2 into 10 power minus 15. It's 0.609 volt. Same, I'm doing this only first iteration. You can calculate by yourself for multiple iterations. Now for comparison, let's take the value closer to 609 in the previous example. So the value closer to this is 654 here. So 651 here. So this means that more current is flown if the area of the cross section is increased for less Vd. Okay, the Ix is 150 here, the Ix is 303 here. That means that double the current is flown for 10 times of increase in area and for the less diode voltage. So that is the comparison. So yeah, That's it for today. We'll do some more problems in the upcoming videos. Thank you. Bye. We'll meet in the next video. Bye.